Welcome to this afternoon session. So the first speaker this afternoon is David Silva from DeepMind, and he's going to tell us about simulation-based search control.
Thank you very much. It's a real pleasure to be here. Really appreciate the invitation. So I would like to talk to you all today about something called simulation-based search control. This is really about trying to understand how to plan. And what I want to convey to you is there's been a lot of advancement in the way that we think about planning, and some very simple and yet powerful ideas that can help to plan in really complex and challenging environments. Okay, so to convey the power of these approaches, I really want to start by telling you some of the work and events that happened when we started looking into these ideas. And to do that, I want to take you back a few years to something that we built called AlphaGo. So AlphaGo became the first program to master the ancient Oriental game of Go. And this was achieved using essentially techniques brought from the fields of reinforcement learning and deep learning, simple ideas brought together in a way that led, for the first time in history, for a computer program able to play one of the most challenging board games that humans have actually devised and played for thousands of years. So just to convey what it was like to be part of this, I'd like to play you this little video. Do we have any volume for this? Sorry.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
So this is taken from
everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness?
Ooh.
Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Well, look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, man, it's got to be a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So it's estimated that around 100 million people watched that moment live where AlphaGo beat this 20-time world champion Lee Sedol. And really what I want to talk about is how can that come about? How can it be that we can build very simple algorithms which are powerful enough, which can plan effectively enough that they can challenge humans and go beyond humans in some of these extremely complex problems, of which Go is just the beginning, really. Of course, we want to reach many, many real-world environments, and I'll talk about that at the end. So there was a particular moment in that game which was known as Move 37, where AlphaGo played a particularly unusual move. It played this stone marked here. If I can try my magic cursor to see if this works. You can see this stone played here. And this was something that no human would ever have done. It played this stone on something called the fifth line, in this diagonal move against this white stone. And to humans, that is just a crazy move. And yet, AlphaGo realized by planning ahead effectively, by really having powerful planning approaches, it was able to understand with quite intuitive understanding that that would lead to this particular encircling over a large section of the board and ended up later on winning the game. Humans were very surprised by this move. They considered it to be quite creative and unusual and something which really changed the way that they thought about the game of Go. So if I just quickly play this. You can see the moment where Lee Sedol here actually comes in and he sees that this move has been played on the board. And you can watch his reaction. he's really surprised by that move, shocked by it. And then he looks at it and he actually starts to smile to himself and think that there's something really interesting there. And when he was interviewed about this move after the game, he said that playing against AlphaGo basically expanded his way of thinking about the game of Go. It led to new avenues, new understanding of this particular game. So that was the game of Go, AlphaGo. But really what I want to talk about is how you can take these essential ideas of planning and make them much, much more powerful and more general. And if you make things more general, they're actually applicable across wide swathes of environments. And so what I'd like to talk about next is something called AlphaZero. And this started with something known as AlphaGo Zero, which learned to play the game of Go completely on its own without any human knowledge. It just started from self-play, played random games against itself, and eventually through this interesting planning process that I'm going to talk about, was able to exceed and vastly exceed the performance of the version of AlphaGo that we just looked at. So the way that works then was actually, it was interesting because when it was playing this game of Go, humans have played the game for several thousand years, and they've developed this enormous store of kind of built up knowledge over many, many years that's passed on by expert teachers. It's studied at universities. And this Go knowledge, has many, many forms. But one particularly well-known form are called these joseki. These are like the corner patterns or the opening patterns that recur in every game. And humans have spent thousands of years developing and deciding on them. And AlphaGo Zero, in just a few hours, actually, through self-play, discovered all of the known patterns that humans played as its training proceeded. It kind of learned through this principled planning procedure which opening patterns are useful and which ones lead to good outcomes. And eventually, it actually learned to discard the human patterns and discovered its own ones, which were even better. And now humans play those instead. So this is a process of when you get things right in terms of planning, then actually it can lead to discoveries which actually feed back into human knowledge. We don't necessarily need to build on human knowledge. If we get the principles right from the beginning, the system can learn for itself, can plan, can figure out for itself from first principles, all of the knowledge that it needs to solve complex problems in complex domains. Okay, so the generalization of that idea that I want to talk about is known as AlphaZero. So AlphaZero, in fact, isn't just applicable to the game of Go, because it's a very general planning algorithm. It's been used in all kinds of places. So for example, when this was first introduced, we applied it to 3 different games. We applied it to Go and also to chess and to shogi, which is a Japanese variant of chess. And what we saw was that in each of these games, after just a few hours of self-play on very powerful hardware, it was able to beat the state of the art, both become superhuman and defeat the strongest humans in those domains, but also to defeat the strongest known planning algorithms that have been developed in each of those domains separately. And in particular, I want to highlight what happened against this program Stockfish, which was the world champion in the game of chess, a program that's had a huge amount of development that's gone into it. And we see here that AlphaZero was able to actually defeat Stockfish. What this little plot at the bottom is trying to show here is that it only lost 0.8% of the game. So just 8 out of 1,000 games that it played against Stockfish were actually lost. So it was a much, much more powerful approach than the traditional kind of planning algorithms that have been used before. Okay. So when you put this together, you see that across these games, this process of discovering knowledge from scratch has led to transformative progress in all of those domains. In fact, many experts have written books where they've tried to understand the way that AlphaZero plays games in chess and in Go, and actually really try to unpick all of these beautiful ideas and motifs and approaches that it's come up with so that humans can actually bring those ideas back into their own play. So to pick just one example of these games between AlphaZero and Stockfish, we see here a particular chess position. For those of you who play chess, you'll see that what happened here is that actually so we have this move here where white has moved its bishop to here. This is considered by many commentators to be the greatest move in the history of chess. This has been one of what's commentated. It was discovered by AlphaZero against this computer opponent. And what it did was actually just throws away this bishop. It can be taken immediately by this pawn. And what happens in this game is that AlphaZero throws away a bishop, it throws away multiple pawns, it gives up just more and more material And in return for what? Well, in return for this long-term influence, this long-term sense that it should be able to get something good out of this position. And eventually it ends up kind of just getting more and more of a stranglehold on Stockfish's position, restricting its mobility more and more and more, and eventually goes on to win the game. So how can this come about? This isn't just a traditional planning algorithm that's looking ahead in some kind of tree search over a few steps and then figuring out how to win the most material. This is really building in, some of the more complex ideas in the way that humans think, understanding intuitions about the game, understanding, deeper knowledge and estimation and approximation about which things could actually work and which things are going to fail. And so AlphaZero brings all of those things together. And if we compare that to what's been done before, if we think about the world chess champion, which came before, it's called Stockfish. And it's really the culmination of decades of research in the game of chess, which was considered the Drosophila of AI. In other words, the organism upon which most research was performed for many decades. So inside Stockfish, it's the culmination of starting with things, the early days of chess, moving to programs like Deep Blue that beat Garry Kasparov many years ago, and finally becoming vastly superhuman. And it has all of these immense complexity in it. It's a very, very clever program, but there's a lot in there. And each of these little kind of terms in here represents, let's say, something like a PhD's worth of expertise that's gone into one single idea. And there are hundreds of those ideas in a typical program. And some of them are domain independent, so very beautiful and elegant ideas that might work elsewhere, but a very large number of them are actually specific to the game of chess and wouldn't work elsewhere. Really trying to build in knowledge that's specific to that game, things like opening books, endgame table bases, specific things that pull in a lot of the human knowledge about that game and into something very effective and powerful. So that was how people used to plan, okay? But we can replace all of that. We can basically throw out the entire thing and replace it with essentially this short piece of pseudocode here. That's the entirety of AlphaZero. And what I want to convey to you in the remainder of this talk is how this short piece of pseudocode over here actually works, what it's doing, so that maybe you can come away with a sense of really how simple it can be to plan effectively in such a way that you can build up all of the intuitions that you need in a simple framework that can be applied very generally, and you can take it and apply it on something new, and out of the box it can learn to recover all of the knowledge that could perhaps have taken humans thousands of years to achieve. Okay, so that's what I'm hoping to do. So to do that, let me say in words what this idea really is. So AlphaZero, this idea, this approach, AlphaZero is an approximate, recursive, simulation-based search. And what I'm going to try and do is unpack each of those terms one by one, and hopefully by the end of this talk, you'll have some idea what that means and understand that this is a very simple idea that can be applied in many, many ways in many places. So I'm going to start at the bottom here. I'm going to start with the idea of search. So search is really all about planning, but I use the term to mean, essentially local planning, planning from a particular state so that from that state, you can perform look ahead and figure out the optimal strategy from that state onwards. Okay, that's what we mean by search. So to do that, we're really going to need to understand the fundamentals of planning. And to do planning, in a principled way, we really need two fundamental concepts. The first of those concepts is the policy. The policy is essentially the object that picks actions, says how should you behave in a given situation. So to do that, you really need a mapping that says if you're in a particular state, what action should you take? And that can be stochastic in general. So a policy is a mapping from a state to a distribution over actions, okay? And the value function is the second key concept. A value function is basically an estimate of the goodness of each state action. So in other words, if I take this state, if I take this action from this state, do I expect to win or lose? How good is it to take this action from this state? It's a measure of goodness of state action pairs. And in general, it's not just about winning or losing. It's about saying how much reward do I expect to accumulate in any environment. And let's imagine for now that that environment is a huge Markov decision process with, in the game of Go, there's 10 to the 170 states. Okay, so something so vast, we can't even consider doing like one sweep across that state space. Okay, so we can have these two ideas, the policy, how to pick actions, and the value function, how good those actions are in particular states. And then we need two processes to corresponding to those two concepts. And those processes are very well known. They're fundamental ideas known as policy evaluation and policy improvement. So policy evaluation simply says, how do I figure out how good those states and actions are? How do I figure out how good is it to take an action from a given state? So policy evaluation is the thing that assigns for each state and action the value of that state and action. In other words, it figures out the expected cumulative reward that you can get from that state onwards. So if you start in state ST and you take action AT, how much reward are you going to get along the way? So think of that as the game of Go. If I start in this state and I play this move here, and we carry on to the end of the game, and I get a reward at the end of the game saying winning or loss, how much reward am I going to get? Okay. And then the second fundamental process is policy improvement, which basically says, how do I improve my policy from the policy I had before pi? How can I come up with a better policy, pi prime, that gets at least as much value from every state and action? Okay, so the idea is to find a new policy that's at least as good as the one we had before. And it turns out that if you do policy evaluation really well, that process of improvement is really straightforward. We simply can, for example, just pick the action that maximizes that value. You know, which action is going to get you the most reward? Which action is most likely to win the game? Well, if you choose that action, you actually improve your policy from the thing that you evaluated before. So that's the two fundamental processes of planning: policy evaluation and policy improvement. Okay, so those two processes can be put together. This is dates back several decades, the idea of policy iteration, people like Howard. And what we see is that we can alternate these two processes. So these arrows are kind of a schematic suggesting the idea that we can start with a particular value function and policy. And if we evaluate our starting policy, we end up with a new value function, something saying, well, how good is it? How good is that particular policy? How much reward am I going to get from each of those states and actions? And once you have that value function, you can improve your policy. You can just pick the actions from each state that would give you the most value according to your estimate. And that gives you a better policy. And once you've got that better policy, you can evaluate it to give you a new value function. And once you have that new value function, you can act by, again, picking the actions that maximize that value to get a better policy, a new value, better policy, new value, better policy. And if you iterate this process, it converges. It converges to the optimal policy, the best possible actions that you can take in that environment, and the corresponding value function known as the optimal value function. So you just need to alternate these two processes forever and you solve the problem. Now, what I want to talk about in this talk is a generalization of this idea, generalized policy iteration. And the key difference there is you don't have to complete any one of those processes. So you can start to evaluate your policy, but you don't need to completely evaluate it. As long as you make a little bit of progress towards that, as long as you move in the direction of evaluating your policy better, you update your value function a little bit towards something which is more accurately estimating the value of your policy, and then you start to improve that. And again, you don't need to complete the improvement process. You can move a little bit in the direction of improving that, for example, just improving it in one state, in one action. And then you can evaluate that process a little bit, improve it a little bit, evaluate it a little bit, improve it a little bit. And it turns out that this idea also converges under very general conditions to the optimal policy and the optimal value function. Now, in general, as I mentioned, the state space is vast. Like, we can't hope to do even one sweep where we kind of do a sweep of policy evaluation across our state space, or a sweep of policy improvement across our entire state space. We can't even get through a fraction of one of those sweeps. So instead, what we can do is we can apply these ideas to individual states and actions. We can update just one state and one action at a time. In other words, we can say, from a particular state and action, how much reward do we expect to get from that particular state and action? That this process here, My mouse appears. Okay, anyway, it's the process, the policy evaluation. And that is going to estimate how much reward you can get from one state and one action. And the corresponding process, we just improve our actions from one state only. So if I'm in a particular state, which action from that state only is going to improve my policy. And so we can do this state by state. We don't have to do the entire state space. We can pick individual states at a time, apply these same processes. And as long as we sweep over all states and actions infinitely often, then this process will also converge. Now, you can hear from that statement that this is going to be a slow process, that if you have to sweep over every state and every action infinitely many times for this to converge, that's going to be a slow process in general. But the order in which states and actions are updated has a huge impact. And if you actually select these states and actions in an effective order, you can, in practice, get extremely powerful planning algorithms that converge very close to the optimal policy and the optimal value function in a very tractable way. Okay, so to understand that idea, let's go back to the traditional approach. Let's think about full width search. So in full width search, this is something like the traditional chess programs, traditional look ahead. You start from some state, you pick actions from that state and consider all of the different possible places that chance could throw you after that. And then from each of those states, you have to consider all of the actions that might happen and all of the places that chance might take you to after that, and so forth. And you end up with this vast search tree if you have a large problem. And we can think of full width search as essentially both evaluating and improving all of the states that are reachable from the root state. So it's a process of search that kind of alternates those two operations that we talked about all the way from the root state. But even a single update, even a single one of these steps, we just think about one of these steps, that might be intractable to compute in a large state space. And that's known as the recursive dimensionality, the fact that if you have a large number of state variables, like the different stones or the different pieces on your board or whatever the state variables are, that the size of the state space grows exponentially with the number of state variables. So you're just never going to be able to do even a single one of those in general, if chance might take you anywhere. And even more problematic is the fact that even if you could do that, the search tree itself grows exponentially with depth. So this look ahead, as you look ahead further and further, you have to do more and more computations. So full width search is essentially intractable in general. And people have done huge amounts of work to prune these trees. That's how something like Stockfish works, extremely clever pruning techniques, but nevertheless, it's kind of a shaky foundation. So instead of that, what we can do is something called simulation-based search. So the idea of simulation is to actually break the recursive dimensionality by sampling. So you don't need to consider all possible things that will happen next. The very simple and straightforward idea is just to sample from those possibilities. So in particular, simulations, a single simulation basically starts at the top of our search, and it just randomly samples an action from our policy, and then it tries that action in the environment, and it randomly samples a chance event from the environment, and that ends up in here, and we randomly choose an action, and we randomly sample from the environment where we end up, and so forth, all the way until termination. And then we do that repeatedly multiple times. And it turns out that if we do this in the right way, we can still preserve all of our convergence guarantees, but have something much, much more tractable. Okay, and it's called simulation because you can think of this as something quite intuitive to the human mind. You can think of this as like imagination, that if the agent has a model of how the environment works, it's like it's imagining what's going to happen next. It's kind of chasing through and simulating in its mind what will happen if it follows this particular trajectory all the way to the end, and then it essentially updates its understanding of the world based upon those imagined trajectories. So now I'm just going to unpick this idea a little bit. So in simulation-based search, we start from a root state S, we pick an action according to our policy, we pick a reward and a next state according to our environment, which I've labeled here epsilon, and we do that again to get another state S double prime. And if we just take away those states and simplify this, we're going to use these pictures to understand the idea. So this is our first simulation on step 2, step 3, step all the way, and now eventually you terminate, and that gives you one simulation. Now, once you've got that simulation, we're going to back up those results. So in particular, we're going to go back to our labels of S and S prime and S double prime, and we can apply our ideas of policy evaluation and policy improvement. And the idea is that we can apply that to all of the states and actions that were visited upon this trajectory. We're going to update those states and actions, and only those states and actions, to make them evaluate the policy more effectively. In other words, we're going to, from each of those states and actions, we're going to update the value towards the mean of what happened. Like, you know, if I got 5 reward on one trajectory and then 7 reward on the next trajectory, well, we update the value towards 6. You know, we're basically tracking the mean. We're updating the value function towards the total reward that we see. So we update this value function. So each of these nodes is going to store a value, and that gets updated towards the total reward from that point onwards. And we do that for every one of these states and actions. And we also improve the policy so that next time we're acting from one of these states, we'll pick the action that maximizes that value function. And if we use these particular ideas, these particular forms of policy evaluation and policy improvement, that leads to a particular form of simulation-based search, a particularly famous one known as Monte Carlo tree search that's extremely powerful and very widely used. But other choices are available. Like, the framework is very general. You can use pretty much anything for your policy evaluation step and your policy improvement step, as long as they really are evaluating the policy and improving it. Okay, so that was just one simulation. Of course, one simulation doesn't make a search. We have to iterate this procedure many times. So that means we go back to the top, and based on the latest information that we've accumulated, we're now going to run another search that makes use of those new values and new policies that we have in the search tree, and updates and updates. So we update to evaluate those states and actions and improve them. And we do that repeatedly to give us n different simulations in our search tree. And it turns out that this procedure, in fact, does converge to the optimal policy for the problem. So it solves the planning problem, but it does so in a way that's extremely efficient. Okay, so I wanted to show you the pseudocode because we're going to build up to the one we saw earlier. So all this means is we're going to have some procedure here, procedure sim, and we're passing in the environment epsilon, value function q, the policy pi. We're going to basically do this. So this pseudocode represents one simulation. I'm not sure I can get this working. But basically what we're doing is we're picking an action from the policy, we're picking a reward, and we can see this, picking an action from the policy, picking a reward in the next state according to our environment. This is just doing one step of our simulation. And then we kind of recurse. So we kind of, so this is recursively calling ourselves to simulate the next step. So this is like, if we're at step 1, we're recursively calling ourselves to simulate step 2. And then as we unwind back through this recursion to compute the total reward. And we store that in this thing G. We update our value function towards that G. So this line is just updating the return, this is like tracking the mean return. We're tracking the mean reward, like how often have I won and how often have I lost. We just update our Q values towards that, and then we improve our policy also based on that. And that's it. That's already a very, very powerful planning algorithm. In fact, this was the first ever algorithm to do well in many complex domains. But we can do even better. Sorry, so this is simulation, this is our policy evaluation, and this is our policy improvement. Okay, sorry, let me move on. So that's the idea of simulation-based search. Simulation-based search is this powerful planning algorithm, starts at the root, repeatedly runs simulations all the way to the end in a principled manner that computes both the optimal policy and the value function of that optimal policy. And it just works, and it's very widely used. But we can do even better. And that's the idea of recursive simulation-based search. So the idea of recursive simulation-based search is to say, now let's allow ourselves to simulate at multiple levels. So previously, we had simulations, these level 1 simulations, these orange things. We had basically one level of simulation. Now what we're going to do is we're going to construct a higher level of simulation out of these lower level simulations. So what we're going to do is we're going to apply our level 1 simulations. So this would be one simulation at level 1, and then we back that up, and another simulation at level 1, and then we'd back that up. And we'll do that repeatedly to kind of do a complicated search, which is this kind of orange triangle. And once we've completed that search, that's given us a really good idea of how to act from that root state of this search tree. So then we take a step. And that step is the first step of the higher level simulation. And then we repeat this process. So now we're at a new state, and we've got a new search tree that's kind of rooted at the at this next state here. And we start running simulations from there. We run a simulation-based search from there recursively. So we run our first simulation from that point onwards. We back it up and update our value function and policy. We run another simulation. We back up our value function and policy. And we do that repeatedly until we've got a really good idea of how to act from this state here. And so now we take a step according to our search that we've run there. We run a complicated search from that, and we take a step. We run our search from there, and we take a step, until eventually we complete our first outer simulation. So we've done all of these inner searches and used that to get very, very accurate steps of this outer simulation. Once you've done that, you can back that up. You can do this multiple times, and it will result in a very powerful 2-level search. And it turns out that you can nest this procedure and generalize this idea to k levels of simulation. So we could introduce a 3rd level of simulation, which calls these level 2 simulation-based search. We could have a level 4 procedure that invokes these level 3 simulation-based search. And you can nest this procedure, and at each level of nesting, every step makes use recursively of the powerful search at the lower level to pick each of the actions that it takes. So that's the idea of recursive simulation-based search. And it's been shown in the past to be very powerful in the sense that each additional level of recursion gives a very big boost in performance. Okay, so if we go back to our pseudocode, we're only adding one new idea in, and that's nesting. We're adding in this idea that at each step of our outer simulation, we're going to recursively call n inner simulations with at level k plus 1. Oops, sorry. At level k plus 1, k minus 1. So we're doing a level k search here, and we invoke our level k minus 1 simulations n times. And that's all. That's the nesting idea. So we're recursively calling many simulations. And that idea is very powerful. And so AlphaZero really is doing a recursive simulation-based search. It actually has the results I showed you had a recursion depth of 2, but you could go more. And the only missing ingredient now is approximation. So what's approximation? Well, again, let's come back to the idea that we're working in enormously complex problems. We want to find solutions that work in enormously complex problems where there's 10 to the 170 states, or where the world is so complicated that we can't deal with it. And so we have a value function and a policy, but now we're going to parameterize those things. Parameterize them in a way that we can learn about all of the states. We can generalize to all possible states when we've only learned from experience of a few of them. And so the way we do that is by using function approximators. In particular, we typically use a very large neural network, or in other words, deep learning. And so the idea is that for this value function, we have one neural network, which you can think of as the value network, which estimates, we feed in a state and an action, and estimates the goodness of this thing. How good is it to be in this state and take this action? And that's your Q theta. That's an approximate value function. And we can do the same thing with the policy. You feed in a state, and it picks an action for you. It tells you, which action should I pick? It's a policy network, an approximation that tells you how to behave from any state. And of course, if we just go to the value function as an example, there's many different ways that we could parameterize such a function. So we could have Our parameters could be set like this red one, and it might behave in one way. We could have this green one, we could have this orange one, we could have this blue one. In general, there's a huge space of possible ways to parameterize your function approximator, like the parameters, the weights of your neural network. How should you adjust those weights so as to get you the right value? And so the idea then of how to do that approximation is to project. In other words, at each step of this generalized policy iteration, every time we try and evaluate something, we're just going to project. We're going to find the best value function in this space that represents this thing as closely as possible. So which parameterization gives the best fit to the value function which we're trying to estimate. So if we've collected all our data, we're trying to figure out what the value is, and then we try and project that onto the space of different neural networks, whatever it is that we can actually represent. And we do that repeatedly. And that's the idea. Now, in general, as with the other ideas in generalized policy iteration, we don't need to do a complete projection. So just as I said before, in generalized policy iteration, we don't need to exactly evaluate the policy, and nor do we need to exactly improve the policy, nor do we need to exactly project the value function of policy. We can do this incrementally, just moving in the direction of the projection. And the way that that's typically done is we take our policy evaluation algorithm that we had before. So here was the non-approximate version, the exact version, where we were just updating our value function a little bit, alpha amount, towards the rewards that we actually saw from that point onwards. So we were in state S, we took action A, and we got all of these rewards. So we can just update the policy a little bit towards that. And now we're going to make that approximate. And the simplest way to do that is to use gradient descent. In other words, we look at the error between the reward that we actually saw, the total reward we actually saw, and our estimate of that reward, Q theta. We take the error between those, say like a squared error, and we adjust the parameters a little bit in the direction that reduces that error. And it turns out that that is a form of incremental projection. If you were to do that forever, you would achieve a projection. So if we put those pieces together, we can approximate in our recursive simulation-based search. We can either choose to approximate using the same theta at all of these different levels, or in fact, we can have different thetas, different approximations for each of these levels of the search. Okay, so in a sense, we're done. AlphaZero is an approximate recursive simulation-based search. And so just to bring that to a close, if we go back to our original pseudocode I showed you and try to convey this sense that there is something really simple. It's not the only thing you could do, but there at least exists really simple planning algorithms which actually solve extremely complex problems with no human knowledge, no extra pieces, no extra knobs and whistles. Here is one, and it's AlphaZero, and it combines simulation, this line here, recursing step by step into the future, with a nested search, nesting just as we saw before in the recursive simulation. In this case, MCTS here means Monte Carlo tree search, so a particular instantiation of that idea. Approximate policy evaluation, and in fact, in AlphaZero, we also use approximate policy improvement. So we project both the value function onto a neural network, and we project the policy onto a neural network. Okay, so that's the end of the technical section. Sorry. So it turns out many other algorithms can be understood as recursive simulation-based search. So there's been a huge variety of research done in this space, including Monte Carlo search, Monte Carlo tree search, Dyna2 and generalization Dyna-K, nested Monte Carlo tree search, classification-based policy iteration, expert iteration, many, many things. And so if there's one thing which I wanted to convey, and which we tried to show in the accompanying paper, this talk, is that there is a unifying framework that incorporates all of these different ideas in sample-based planning and how to plan with simulations. Sparse sampling should have been on that list as well. Okay, so just finally, if we go back to this evolution we saw, we started with AlphaGo. We showed how that could progress to an algorithm, AlphaZero, that starts just from self-play, plays against itself, no knowledge, random initial parameters, plays and plays and plays. And that process of planning can be understood as, that process of self-play can be understood as the simulations in this simulation-based search at an outer level, and it does these inner level searches. Okay, there's one final step I wanted to mention, which we did most recently, and this is the step towards an algorithm called MuZero, and the key step there is to actually learn the rules of the game as well. So in all of the previous example, the rules were known. So now we're going to take away the known rules and see if we can end up with an algorithm that not only starts from scratch in terms of its parameters, it also has no understanding of how the game works. All it gets to do, it's like it's playing chess against someone and like tries to stumble across some moves, and eventually it sees that it lost the game and it gets a 0, or it won the game and it got a 1. And it has to figure out which moves are legal, how they work, how the game is scored at the end, all the rest of it for itself. And if you can do this, you can apply it much more generally in domains with unknown dynamics, the real world. The real world has that character. We don't know that a useful expression of dynamics that an agent can plan with in the real world. Okay, so MuZero. So when we took this idea of starting from scratch, not even telling the system the rules of the game, how did that pan out? Well, you might think it would slow the system down a lot, because now it actually has to figure out the rules of the game as it goes. But it turns out that when we applied this to chess, shogi, and go, it reached the same superhuman level of performance that we saw earlier with AlphaZero, the version that knew the rules of the game. And it did so in about the same time. It was still very, very efficient. It was able to learn the rules as it went and master the game. And what this allowed it to do was to work in much more complex and messy environments where it's hard to specify the rules. So we tried this in a suite of video games. We tried this in all of the Atari 2600 games. And it turned out when we did this, it actually outperformed the state of the art by quite some margin. In fact, we did this a few years ago, but it's still the state of the art in that domain, which is a standard benchmark for reinforcement learning. So it's a powerful idea. It works very generally. Just one brief slide explaining the idea, because all it takes is a generalization of this idea of value function. So before, the value function was estimating how good is it to take action A from state S. Now we're saying how good is it to start an state S and take a sequence of actions A1, A2, A3, and so forth. And it estimates the value of that whole sequence. And if you can estimate the value of that whole sequence, then this allows you to plan ahead and say, well, if I was to take this sequence over here or this sequence over here, then I know I've got an internal estimate of how good that would be. And the magical part of doing this is that inside this function approximator, it constructs a model of how the world works. So the rules of the game are represented inside that function approximator in such a way that it helps the system to accurately estimate how good it is. In other words, you can only estimate whether you're going to win a game of chess if internally, inside your mental model of how you're evaluating this thing, you're actually able to understand that if I take this step, then this step, and this step, I'll end up winning the game. That requires that internally you've built some sense of how the rules work. And it might not correspond to the real world rules, but you've built a consistent representation of how the world works inside your own head as the agent. Okay. Right. So finally, applications. So I mentioned at the beginning, this is not just something which has been applied to games. Once you build a very general, powerful planning algorithm, it could be used in many, many places. And in fact, many other people have taken these ideas and built upon them. And so we have exciting work from all over the place. So just to highlight a few examples of many. So Arwin Segler and others had a fantastic Nature paper where they applied AlphaZero to actually figure out chemical pathways to do synthesis of chemicals. Dalgard and others applied AlphaZero to actually beat the state of the art in kind of an important part of quantum computation is understanding this quantum dynamics function. And they found that AlphaZero did a much better job of that than any past approach. In DeepMind, we applied AlphaZero to the problem of video compression. So it turns out that video accounts for 50% of the bandwidth across the entire internet. And by applying AlphaZero to the codecs which are used to compress videos, they were able to save something like 2 or 3% of all of that video bandwidth by compressing videos in a more efficient way. And finally, at the last Tesla AI Day, it was announced on their videos that they are actually using an algorithm that's essentially the same as MuZero in the self-driving car, or at least in some of their research prototypes. So AlphaZero can be used very widely, or the variants of AlphaZero. And thank you very much for your attention. I hope you found something there useful.